So chemistry is the study of matter, but energy affects matter. Energy changes are what drive a lot of chemical changes. So what is energy? Energy is anything that has the capacity to do work. So work in science is defined a little differently than work in real life. Work in regular life is, I went and I did something and I got paid for it, right? In science, work is a force acting over a distance. So here's my calculator on the bench top, and if I push it across the bench top, I did work. Now, did anybody give me money for that particular action? No. But that was work. I exerted a force, and I moved something through a distance. So energy is the capacity to do that. So energy is equivalent to work, a force acting through a distance. So heat is a flow of energy that's caused by a difference in temperature. So we know from life experience that if you put a cold thing and a warm thing together, the cold thing will get warmer, the warm thing will get colder until they get to be the same temperature. That's heat, the flow of energy. Energy can be exchanged between objects through contact, for example, a collision. If one thing collides with another, it can transfer its kinetic energy to the other object and send it flying. We also get heat, that flow of energy, through contact. So we need to think of energy as a quantity that something can have or possess. So I found that energy as money is a very useful analogy. So heat and work are ways that an object can exchange energy with other objects, but energy is something that the object has. So energy can move out of an object or it can move into an object. So your wallet holds money, right? Money can come into your wallet, money can go out of your wallet. The process of it coming in and leaving is equivalent to heat and work. The energy is the actual money. It can move back and forth. There are different kinds of energy. Kinetic energy is the energy of motion. Thermal energy is a kind or a subset of kinetic energy. Thermal energy is associated with the temperature of an object. And so as a temperature, it is the average kinetic energy of the particles. The particles in a substance are always moving, even in a solid. So this benchtop seems pretty stable, right? But the particles inside of it are vibrating. They're moving back and forth. They are so tiny, and the scale on which they're moving is so small that we can't perceive it with our senses, but they're moving, okay? If we warm up the counter, the benchtop, we make the particles move faster. So the temperature has risen because their thermal energy has risen. It's kinetic energy. Any questions about that? Here we have an illustration using a billiard table. So we've got these billiard balls, and here's the cue ball, and it's traveling across the table and it's going to hit this purple ball. This white ball, because it's moving, has kinetic energy. It's moving through space. When it collides with the purple ball, we know what happens, right? The purple ball is going to go shooting off, and the white ball might actually just stop, or sometimes it'll just kind of dribble off in one direction or the other. The white ball has transferred its energy to the purple ball. Now the purple ball is the one that's moving and has more kinetic energy. The process of it transferring energy from the white to the purple is called work. So the white ball did work on the purple ball. The energy is what the ball has. The work is the transfer of the energy from one ball to the next. The other broad category of energy is potential energy. So kinetic energy, energy of motion. Potential energy is energy stored in an object or energy associated with the composition and or position of the object. So if I hold a Sharpie out above the floor, it has more potential energy than it does if I hold it down at my side. So if I let go of it, what's going to happen? It's going to fall. Every single semester it does that. It falls. As it fell, it went from really not moving much in my arm, and as it fell, it went faster and faster. It also got closer to the ground. And so as it got closer to the ground, its potential energy decreased, its speed, its kinetic energy increased. So positional potential energy was being transformed into kinetic energy. Now, what happens when it hits the ground? What happens to all that energy? It's got to be transferred. Energy is conserved. We can't gain or lose, create or destroy energy. It's transformed into heat, thermal energy. Okay? And that's not immediately obvious because it doesn't feel warmer. But when two really massive things collide and stop moving, there's actually detectable heat that's generated. It's transformed into heat energy. Chemical energy is a kind of potential energy, and it's associated with the relative positions of electrons and nuclei in atoms and molecules. So here we have an illustration of dropping a billiard ball. So here the ball has gravitational potential energy, because if we let go of the ball, gravity will exert a force on it. So the ball will fall. As it falls, it loses potential energy, gains kinetic energy. So this helps us to understand the organization of these different types of energy. Energy is the capacity to do work. We've got kinetic energy and potential energy. Kinetic energy is due to motion. Thermal energy is a form of kinetic energy. It's associated with temperature. It's the movement of the individual particles within the object. So kinetic energy, when you throw a ball, the ball has kinetic energy moving through space. When the ball is just sitting in the grass, it does not appear to have any kinetic energy. And yet it does, because the individual particles are moving. Then we have potential energy due to position or composition. What we're most interested in chemistry is chemical energy. And here we're not looking at, how far the marker is above the ground. This chemical energy arises from the positions of the charged particles inside of atoms. So positive protons, negative electrons, how are those arranged? That gives rise to chemical energy. Any questions? Here's some other forms of energy. There's electrical energy. This is a type of kinetic energy that's associated with the flow of electrical charge. Electric current is the flow of electrons. It's electrons moving through a wire, right? It's motion, so it is a form of kinetic energy. We've been talking about heat or thermal energy. This is the kinetic energy associated with molecular motion. There's light energy, also called radiant energy. And this is kinetic energy that's associated with energy transitions in an atom. And we'll talk more about that in Chapter 7. There's nuclear energy. This is a form of potential energy. It's potential energy found in the nucleus of atoms. So in a sense, nuclear energy is also chemical in nature. So chemical energy is a potential energy due to the structure of the atoms, how they are related to each other in a molecule. So the law of conservation of energy states that energy can be neither created nor destroyed. So we can't make new energy. We can transform energy. We can find energy and make use of it. We also can't destroy energy, but energy can be lost from a useful form to a non-useful form. So whenever we transfer energy between objects or convert it from one form to another, the total amount of energy present in the universe is going to be the same. So here the woman is applying mechanical potential energy by pressing this ball down on a spring. She's putting energy into this to compress the spring. When she releases the ball, the spring springs and the ball flies up in the air. And energy has been transformed. There's no loss of energy. If we think there's a loss or a gain in energy, it just means that we haven't looked in the right places. So when we're talking about energy, we need to talk about a smaller piece of the universe than the entire universe, right? And so we define the system and the surroundings. The system is what we're studying, the particular part of the universe that we're interested in. It could be a chemical reaction occurring in a styrofoam coffee cup. We'll be doing that in lab. It could be anything. We can define the system any way we want. The surroundings is everything else, technically the entire universe. But practically, it's everything else that the system could possibly exchange energy with. And what we're studying is the exchange of energy between the system and the surroundings. How many of you guys have had physics, even in high school? Several? Okay. So I don't know if you came across this in physics class, but position of an object. How do you measure the position of an object, where something is? You measure it relative to something else, right? In physics, your mind kind of gets blown a little bit when you realize that everything's kind of relative. Like, how fast are you going if you're running down the street? Well, are you talking about how fast are you going relative to the car driving next to you? How fast you are going relative to the Earth, which is also moving. The Earth is spinning and the Earth is moving through space in an orbit. What do you call zero? What is zero speed? You kind of have to just say, well, this is what we're going to reference everything to. It's the same thing with energy. It's very difficult, maybe even impossible, to measure how much energy an object has. But we can look at how much energy relative to something else. And so that's what we're looking at, is the exchange of energy between the system and the surroundings. So here they've illustrated this sort of like a gas gauge. So here's the energy gauge for the system, the thing we're looking at, the energy gauge for the surroundings, everything around it that it could exchange energy with. Now, if I'm looking at a beverage in a cup, I've got ice cubes and I've got the beverage, and I'm looking at how cold this is. It could be exchanging energy with the cup, and probably either with my hand or the air around it. This is probably not exchanging energy with a snowbank in Minnesota, right? That's just really, really far away. And anything occurring there is so infinitesimal, we don't need to worry about it. So we would just be looking at the system as the beverage and the surrounding as things that were nearby. So here we have our system with a half full energy gauge, and the surroundings, that's 1/4 full. And there's an energy transfer from the system to the surroundings Now the system has gone down in energy, the surroundings have gone up in energy. The surroundings gain the exact amount of energy that was lost by the system. So if we think about this in terms of money, if I pull $5 out of my wallet and give it to you, and you take it, right? Was any money lost in that process? Well, I transferred money away, but he gained it. That $5 is still $5, right? So that's how it is with energy. It's not that when I hand you a $5 bill, now it's only worth $4.50, right? That doesn't happen. Any questions about that? So what's lost by the system is gained by the surroundings. Now that could look like me, if I'm still, paying out $5, it might be 5 $1 bills, and I give 3 of them to you and 2 of them to you. I have still lost $5, and my surroundings have gained $5. It's just in different forms maybe and spread around. But the $5 still exists. So energy is something that can be measured, so of course we have to have units. Kinetic energy, we've seen this equation before, is 1/2 the mass of an object times its velocity squared. So the amount of kinetic energy is directly proportional to its mass and the square of its velocity. So that can give rise to energy units. The SI unit of energy is the joule. It's spelled kind of funny. It's named after a scientist, Joule, pronounced jewel like a jewel in a crown, and the abbreviation is capital J. This is a relatively small unit. Just, for reference, here's a light bulb. A light bulb is going to use about 3.6 times 10 to the 5th joules in 1 hour. It's only 0.1 kilowatt hours, which is another unit of energy that the PG&E uses. So the unit joule, we can put metric prefixes in front of it. Kilo means 1,000 or 10 to the 3. 1 kilojoule is 1,000 joules. The unit joule comes from that definition it comes from a definition of work and also a definition of kinetic energy. So we said that energy is the capacity to do work. Work is a force exerted over a distance. So Newton is a unit of force, and meter is a unit of distance. A joule is equal to a Newton meter. I'm explaining this to you just because I think it's helpful to understand that all of these units in the SI system work together. Not going to test you on these kind of sort of strange units. So a Newton is equal to a kilogram meter per second squared. Meters per second squared, if I remember correctly, is acceleration times a mass, and that's a force. And so when we take that and we multiply it by meter, so that we get meter times Newton, then we get kilogram meters squared per second squared. And that's what a joule is. If you think about mass times velocity squared, right? So mass being kilograms, velocity being meters per second squared. So kinetic energy is 1/2 the mass times the velocity squared. So that's where all these units are coming from. So joule is a unit that we'll use, and calorie is another unit. You're familiar with calories, right? Because people talk about those all the time. There are different kinds of calories, though. So a calorie with a lowercase c abbreviated lowercase CAL, is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. So this is a different sort of a definition than the one for the joule, which is 1 Newton times a meter. So the amount of energy needed to heat 1 gram of water 1 degree Celsius. So there's a relationship between calories and joules. A calorie is 4.184 joules. That's an exact conversion, so you're not going to lose any sig figs doing that conversion. The calorie that we're familiar with in everyday life is a nutritional calorie, and that has a capital C, and it's a capital CAL, and the nutritional calorie is equal to 1 kilocalorie with a small c, 1,000 of the small scientific calories. Okay, this is confusing. I'm sorry, I wouldn't have done it this way, but I can't change what the rest of the world is doing. So if you see an exam question and there's a capital C, exam questions are typed out, and it should be clear. This is a capital C, this is a lowercase c. I do not make typos like that. Okay, it's not a typo, it's a capital C. That's a big calorie. Big C, big calorie. It's 1,000 times bigger than the little calorie with the little c. Here's some energy conversion factors. I will give you this calorie to 4.184 joules. We don't really use that often enough for you to really remember that, and so I'll give that to you. You should be able to remember that a kilocalorie is 1,000 calories, because that's just a metric unit thing, okay? Here's a kilowatt hour to joules. It might come up in a homework problem, but otherwise we won't be using that. Just for some idea of how big these units are, we've got some different activities here. Amount used by a human body in running 1 mile, expressed in joules, scientific calories, nutritional calories, and in kilowatt hours, sort of just for your interest.